my name is Andrew Robesso, and I am a computer engineering student here at UCF. I'm responsible for designing the circuits that connect the microcontroller to the rest of the circuitry and the software that controls the microcontroller peripherals.
Hi, I'm Noah Watts, and I'm a computer engineering student. I worked mostly on the note detection algorithm and code, as well as the analog preamp circuit.
My name is Colin Smith. I'm a graduating electrical engineering student at UCF. I provided support for hardware design, and I was responsible for the schematic and PCB layout, as well as testing and integration for the Polyphonic analog to MIDI converter device. Our main goal for this project was to apply what we've learned in school to create a device that blends our interests in electronics and music. The potential impacts of our project include changing the way some musicians think about their studio or live setups. The device we've created digitizes analog audio signals from an electric guitar and encodes that information into a MIDI stream for use by MIDI-compatible devices, such as digital audio workstations and synthesizers. This kind of technology can open up a lot of creative possibilities for use with other tools. We may even choose to pursue this device further after graduation to refine the design for public consumption.
We were motivated to pursue this project because of our common interest in music. In order to make sure we met the main requirements of note accuracy and latency, we created two tests. The first test for note accuracy simply required us to plug a guitar into the device and record the accuracy of the note conversion when single notes, triads, or full 6-note chords are being played. The second test was to attach oscilloscope probes to the analog input and the digital MIDI output of the device and record the time difference between the first signal received by each probe. The results of these tests showed that we had over 80% accuracy for single notes, which was our target, but about 50% for chords, which was low, but something we could work with, and a delay of less than 50 milliseconds, which was far below the 100 milliseconds requirement that we set. And this is a encouraging metric that suggests that we could reduce it to a level that would be suitable for live performance. During implementation, we had to test the pins of our ICs and make sure they were connected to the right pads with a continuity check. We loaded test code onto the MSP430 to exercise some of the I/O pins, ensuring that the processor was working and that the pin connections were correct. Finally, with our program loaded onto the processor, we hooked up a guitar and tested it out, making sure that the preamp section was amplifying and filtering correctly. The note detection algorithm was picking up the notes played on the guitar, and the MIDI output circuit was sending usable MIDI data to the MIDI output port.
Since one of our main goals was for the device to have minimal latency between input and output signals, our note detection algorithm focused on optimization. To do this, we took a frequency domain analysis approach that required heavy harmonic analysis and manipulation to be able to detect the fundamental frequencies of the notes being played. To reduce the latency of all the computation and processing required, we minimized memory usage and avoided complex computations such as division or square roots. Instead, we heavily relied on right and left bit shifts and additions to perform very fast approximations of the calculated values. Our entire project was designed and tested over online calls up until the final integration phase. We were able to accomplish this by having weekly online meetings. Our weekly meetings often included planning and division of workload, as well as occasional group work and design sessions. We also made time for extra meetings as needed to make sure we stayed on track and maintained a steady pace. One of our motivations to see the project through did include the daunting aspect of our graduation depending on it. There was also much more personal motivation for all of us. That reason being that we're all very passionate about music, engineering, and design, so this project was genuinely exciting and fun for us to all see through.
One major difficulty that we faced was the loss of our teammate Sean. We expected to have 4 people working on this project, but we lost contact with Sean in September. We don't know what happened, and we hope he's okay, but his absence did mean that we didn't have the manpower to create a case or implement certain features in the allotted time. The biggest takeaway from this project that we can apply to our work in industry is to always have a design review. It doesn't matter how small the design is or how insignificant the changes you made are, you always have to have at least 2 sets of eyes review it. As good as we were about meeting regularly, we didn't really scrutinize each other's designs very closely. This led to an issue in the power section that fried our entire first PCB due to a short circuit. We ended up needing to use an off-board power supply because we couldn't implement a new power design in time. If we had done a proper design review for that power section, this could have been avoided. Alright, that looked like a very clean C major chord. Let's take a look at it. We're looking for 4 notes. We've got C, G, C, and E. And that's our chord.